Yeah, let's get started. So it's 5 minutes past 2:30. Hello everyone. I'm very glad to speak here to all of you. So today the my talk is around generating from generative language models. So before I go to the talk, I'll briefly introduce myself. So my name is Jiawei Zhou, or you can call me Joe. So I'm a new assistant professor here at Stony Brook, joining this year. My background was more on the neural NLP side. So pre-LM, I did a lot of these core NLP problems. But now my general research goal is to build these intelligent systems with deep understanding of language and also plus other modality so that we can get like more intelligent machines to solve a lot more problems. So along the way, you get a better feeling of what I mean by these. Okay, so today we're living in the era of large language models and generative AI. And in fact, the concept of generative AI stems from the general kind of generative power of these large language models as they came into being. So here, the images are actually generated from these generative AI tools. So if you use them, they may look familiar to you. So on the left, so this large language model, I asked the Gemini to generate image for large language models and give me this. So the large is not displayed, but the whole object is pretty large. And then asked it to generate generative AI. It didn't have any clue of like how to make that concrete. So it just generates the words generative AI. And we see a lot of efforts in the recent years putting into making these models bigger and bigger. So here is a plot of like scales of these models when they how they increase of the along with the years. So we see that especially ever since ChatGPT came out, there's a race to make these models ever larger so that their capabilities become stronger. Um, so what can these models do? There's no question that these models are great. So here again, some illustrations from some of the most advanced Gen AI models. So here I asked both Gemini and GPT-4o to give me some illustrations of showing the applications of large language models. Seems the models are trying to express what they think in a very, very abstract way. But you get the ideas. So probably it means that, these models can do translation, creative text generation and so on. But basically LLMs nowadays have covered a wide variety of applications and usually to a degree of showing some kind of intelligence that can help us actually to achieve many things in our daily lives. So here's a more kind of normal diagram to show, these example applications. So I believe by this time, everyone has had some experience of using large language models. So they can help us do a lot of things from just doing conversation agents, help us translate, answering questions of the world, and or even write code. And moreover, there's a huge amount of investment around the applications of large language models from the model development, productizing these models for daily service and to building reliable and scalable systems and infrastructures that can support these models to support to serve everyone. So why these models are so powerful? What are the building blocks of these generative AI or large language models? So here, again, because the talk is around that, so I still ask these large language models of what they think or what they can give us about why they're so powerful. So from both Gemini and GPT, they gave pretty much the standard answers that I believe many of you have already seen over and over again. But putting that aside, so these generations are actually quite good, not only on the fluency level of of the language, but also on the contents as well. So they both touch on many important factors, like scales of the data and parameters, transformer architecture, unsupervised or self-supervised pre-training, and so on. And by the way, so it looks like in this case, the text generation qualities are still much better than the image generation qualities for this illustration. So in this talk, this is also going to be our main focus when, even when we speak about multimodal generation, we mostly focus around generating text or generating structures that are closely related to text. So these are all amazing, but when we talk about large language models or just language models, what are we talking about? So what are these models and how do they work? So here, I just want to briefly give an overview of the basic ideas behind these intelligent machines or so-called intelligent machines nowadays. And these basic ideas actually are extremely simple. So first, next token prediction. So this applies to both training and inference. So essentially, a language model is just a probability distribution with some parameters that tries to assign a probability score to any given strings or sequences. And this can also be decomposed to the products of predicting the next tokens or a sequence of predictive distributions in this form. So here X, they represent a token sequence. And with this simple objective for modeling and also generation, so next token prediction is applied to both the model learning or training process and also the generation process, or we call decoding or sampling. So during training, you have a lot of, let's say, text data, and you feed in the data and compute the loss like this, and you update the parameters so that the model can fit in the distribution of the ground truth data. And during generation, you're given the model, and then you generate the tokens one by one based on this predictive distribution. So here's an illustration. So given a language model, you can generate text in this way. So you give it some prompt or some prefix, and the model can fill in the blank, basically. In this way, the model is powerful enough to tell us this probably should be a token language. And even with the model nowadays very capable, so even you have very, very long context and can successfully generate the next token to very in a very faithful way. So in this case, it will comprehend all of these and generate a next token being text. Okay, so next token prediction, very simple, but very effective. And next, we have the transformers. So almost most of the advanced large language models nowadays are built on these transformer architectures. So they're roughly speaking, they're composed of these stacked layers of encoders and decoders. And modern LLMs are basically on these built on these decoders only. So, and within each layer, we have this attention mechanism, basically trying to synthesize information from input at different locations, and then recursively applying this, and the model builds up some semantic representation along the way so that we can do more interesting things on the top layer. And there are some subtle differences between the decoder and encoder. So most of the transformer models behind these large language models are decoder only based, so that they can generate tokens one by one. And since the transformer models came out, they kind of revolutionized the language modeling research at scale. So one reason is that they can allow better parallel training, because in this case, previously we were just using models like LSTMs or RN models to train these to build the language models, where for training it's very slow because you have to compute the semantic representation step by step. But for transformers, you can basically parallel that. And also they have better GPU compatibility because everything is in this matrix manipulations. And with modern hardwares, we can make this scalable more easily. So putting these things together, so we have an autoregressive language model, what that means. So at inference time, the model give us these predictive distributions. So basically based on the previous tokens, you can generate the next token. And for example, let's say you want to generate this sequence. You have this language model. You can start from the first token, and then you pass it to the model, and model computes the distribution, and then you sample from distribution, you get the next token, and then you pass that token back to the model, and then you generate the next token. And this process could continue until you reach to the end, or you let the model stop. So that's how most of the modern LLMs do when they do the generation, and also when they train their models. So the generation is also called decoding. So we talk about large language models, but why does it have to be generative? So in fact, in the name, there's nothing indicating that this model has to be a generative model. And in fact, large language model can be a general representation learning tool that doesn't have the ability to generate. But the ability to generate is just so powerful that can enable this model to do many more things. So what are we talking about when we talk about generation? If you think about models with bidirectional attention or BERT-like models, they're good representation learners. They can do a lot of classification tasks. When we talk about generation, they're essentially also doing classification. It's just they classify on a different space at different granularity. For example, if you have these language models, basically they generate you some kind of semantic representation, H, and then you pass that through some projection onto the vocabulary, and you get this distribution. So although we write as a distribution, so it's actually a discretized distribution. It's doing this classification problem on the tokens in the vocabulary at every time step. And why this makes it so popular? Because it provides us a ubiquitous framework towards all different tasks. For example, previously we had this different model architecture for doing different things for classification, question answering, sequence for machine translation. But now you can just use the same decoder-based large language model to do all of these tasks by just generating the next tokens. For example, you can do question answering by just providing, the question, and then let model continue to generate the answer. You can do task classification. Here, you can just ask the model what's the label, and then the model will generate a label for you at the next position. You can do summarization. You can also do content moderation, and so on. And next, we call these large language models, but there's a term language in the model, but today the scope of these large language model already goes beyond the language applications. And in fact, in the next token prediction, transforming these basic building blocks, there's nothing specific to language that says these models can only or has to be tied with language. And in fact, there were a lot of discussions recently also in the online forum. So here's a post from Andrew Karpathy saying it's a bit sad and confusing that large language models have little to do with language. So he was trying to think if we can have a better name. And Yan LeQuinn also said it only works with discretized outputs. But actually any discretized outputs can be modeled by these language models. And there are even more discussion. Ilma said, definitely needs a new name, but some people call it multimodal LLM. It says it's extremely silly because the first word multimodal contradicts with the third word, which is language. But still, we call it that way in many cases. And there's another proposal to call it large neural networks, which I think is pretty good as an accurate name because we currently apply these models to many different places. So in today's talk, I'm mostly going to talk about a few kind of techniques and applications around the idea of generation with these transformer-based models. So generation is a core capability that enables these models to do a lot of fascinating things. And there are many challenges still. For example, the generation quality, we want the model to be trustworthy. We don't want to hallucinate in many applications. We also want the model to be adaptive to the new information in the dynamic world. We want them to be fast because auto-regression generation is limited by their sequential nature. We also want them to incorporate these multimodal information, like generating general sequences like DNA or some of the sequences in chemistry, all incorporating multimodal information like images and videos, audios, and so on. So I'm gonna talk about three different applications, or more accurately, three different decoding algorithms that we built towards these different applications, hopefully to provide a unifying view of these large language models, or generative large language models, and showcasing what they are capable of doing. So in the first one, we're going to talk about this general kind of text to graph generation. And the second, we're going to talk about how to improve these LLM generation quality and efficiency with a novel algorithm at inference time. And lastly, we're going to touch upon briefly on improving the quality of multimodal generation in these vision language models. Okay, so in the first part, we talk about generation for a different modality other than language, which is a graph. So what do we mean by graphs, and why do we want to generate these graphs? So I'll start by giving an example. For example, I like eating chocolates, and they're very colorful. And there's a saying like, life is like a box of chocolates. You never know what you're gonna get. But I would claim that language is kind of like the box outside the chocolate. So no matter which different boxes you get, you still get the same kind of chocolate made from same materials like cocoa beans. So language, they express meanings with their surface form. For example, you can look at the sentence, the boy sends a box of chocolates to the girl. You can express it in many different ways. For example, the girl receives a box of chocolates from the boy, but essentially they have the same meaning, which can be depicted by this cute picture. Or you can use a graph, which we call a semantic graph, to represent this kind of meaning from these different variations of surface form of language. So natural language, as the communication tool, has a lot of variations on the surface form, but the meaning is usually abstract, a little bit more abstract, and also more formal. So going from the variations from language to the meaning, sometimes we can use these semantic graphs built by people to help us better or more accurately interpret their meanings. So here I want to take a very broad view of these graph structures. We call it semantic graph, but in this kind of setup, it could be any kinds of graphs. So usually there are these general constructs with nodes and edges, which both could have labels. So we could have labels on nodes and labels on the edges representing the relations between the nodes. And depending on the usage and application, we could have different types of graphs. For example, some semantic, abstract semantic graphs, which we saw before, or some kind of executable semantic graphs, which can also represent functions in code, where each node can be some function names or their values, and the edges can represent the argument relationships. So being able to generate these mini representations in the graph format from language reduces the variation in the surface form of the language, and it allows machines to utilize a more unified and accurate internal representation of semantics for different purposes. For example, many AI systems utilize these kind of graph representations of semantics in their reasoning. So here are some illustrations of for example, application in formula search, in common sense reasoning, multi-document summarization, or even visual scene understanding, where you can build these object type relationships explicit to help more explainable reasoning. But despite being useful for many applications, so these abstract meaning graphs can often become arbitrarily complex because they try to extract the meaning from the language, which could have a lot of subtleties. But we still have to have a high accuracy in these graphs whenever we want to automate the process of generating them. So how do we do this? So before we talk about the decoding algorithm, I want to briefly introduce one type of these semantic graphs as an example for our study. This is called abstract meaning representation. So details don't matter that much, but roughly speaking, so it's a semantic graph where we could have nodes representing, the objects and subjects, and edges representing the relations between these entities. Actually, to annotate this graph very well, you have to combine many different NLP tasks like word sense disambiguation, semantic role labeling, among others, because these label informations, they actually represent that different types of information. So our goal now is to generate this graph from the sequence. So people have tried many different approaches. So without going too much detail, so here are just a few kind of categories of these approaches. Some of them try to build these so-called transition systems that translate these graph construction into some special actions, but they have limited coverage because that doesn't cover all different types of graphs like beyond DAG and so on. And some of them are more graph centered. They use maybe graph neural networks and other things to formulate these graphs as a sequence, or some other approaches just take the literal way of just linearizing the raw data in the graphs and just use whatever transformers we have, but they don't have the structural guarantees because in the generation, you could generate EO form graphs and then you have to do post check. In our case, we propose some kind of broad coverage end-to-end and structure framework for generating these graphs from text accurately. So, so on a high level, like how we speak a sentence word by word, we could also generate these graph components one step at a time. So for example, if we have this graph as our goal, we could formulate this generation process of each time generating either a node or an edge. And we have some rules, like for example, we only generate a new edge until all the previous edges are generated, and so on. So without going too much detail in there, so here's an illustration of how we can build this autoregressive graph construction process. For example, we generate the first node, and then next step, we generate a second node. And now, because we know there's an edge between them, and then in the next step, we can just construct the edge and close all the edges that can exist between the currently available nodes. And now, because there's no new edges, we move on to the next node, and then we generate the new edges and so on until we can complete the graph. So basically, we formulate this graph generation problem, which has its structure to still an autoregressive sequence generation problem based on these construction actions. And this process can actually apply to any graph without limitation of the structures. And we formulate these sequences as so-called action sequence, where each action you can think of that as some kind of tokens in the vocabulary, but now they have their meanings linking to the graph construction process. So here is some brief overview of the action sequence we use. But basically, we have some of these actions that control the movement of the scanning process of the sort sequence, some of the actions that take care of how to build the nodes. So they have their specific meanings, but I'll just speak about the general category. Some actions take care about the edge generations because for each edge generation, it's actually a composite action because you have to generate the label, the direction, and also which node you want to connect this current node to. So with these tools, so the generation would look like a sequential process in the following. Let's say you have this sequence and you want to generate these AMR or semantic graph. We first maintain some kind of cursor. So we scan the sentence from left to right, and at different places of the sentence, we can generate different nodes, linking that node also to the source. Because these semantic graphs, they do not kind of exist without the sequence. They have some kind of loose connections with the sequence. So we want to build that alignment connection along with the generation. So we first look at the token, and then so this reduce action basically means we don't do any action towards the graph. And the boy, we simply copy this to the label and generate a node. And next we shift, which means we look at the next token. So you can also think about these, the movement of the cursor as some stack and buffer structures, but not quite exactly. And then next, we can generate once another node from the token want. So here you directly predict the label of this. And now we have these two nodes. So based on our generation rule, so you can generate an edge between these two. So the next action is actually generating this edge. So here you generate
the prediction part. Can you explain what happened here? You shifted, then what happened?
I shift, and then I make a prediction of the node with label want-01, because in the case of boy, so the node literal label is the same as a token, but this one I also predicted the label here. And now with the edge, we have so this represents the left arc, so some direction, some label, and then so this basically connects the most recent generated node, which is 1-01, to a previous node that's labeled by its index here. So here 2. So here we have 2 here. So we have this pointer mechanism that can link the edges to guarantee the structures. And then we close this edge, and then we shift and move to the next place. We move to the next place, and we can generate another node, another edge, and another edge, and so on until we can complete the graph generation process. So basically, this process utilizes these action sequences to produce the graphs in an autoregressive way, like how you normally generate language from these models. And with this, yeah. So in the 2, because 2 doesn't convey, so in this formulation of graphs, 2 doesn't convey any semantic meaning, so it doesn't go to the graph. So I just ignore it. So we have this reduce action, which means just reduce it, just don't do anything there. Yeah. So basically with this framework, you can generate any graph in an autoregressive fashion. And you also link the text for graph construction, because every node or edge generation can be attributed to some construct in the sequence. And also you can enable some end-to-end training systems. Here we use transformers. So basically during training time, you can have the graph, have the text. You also have the alignment. You can transform the graph's data structure to a sequence of actions. And with the encoder-decoder transformer, you can train these model by producing these action sequences from the source sentence. There's a little bit caveat because in generating the edges, we actually use the pointers to tell us where to connect the edges, because the edges, the nodes are actually connected to each other. So to generate that, we use something called, we directly use the self-attention. So the self-attention roughly computes distribution over the history generation tokens. We repurpose that self-attention to help us predict this kind of pointer values of a previous position or node to link the edges. And also we also inject some structural bias into the cross attention to tell us where to look at in the source sentence to generate the next token or next action token. So these are just technical details. For more details, you can check our paper. But with these kind of structural kind of formulation and also injection into the transformer attention, we found that our approach actually achieved much better than the previous ones. For example, this task is AMR parsing, which is to generate these AMR graphs from natural language sequence. And the y-axis is a evaluation metric, basically measures your model generated graph, how much it overlaps and maps with the ground truth. And this is considered a kind of a low resource setup because it's very expensive for linguistic experts to annotate these graphs. We have about 30K training examples for this data set. And later we could also even use pre-trained large language models. At the time, so it was a few years ago. At the time, it was considered large, but nowadays it was not. So it uses sequence model called BART, which were pre-trained to producing language sequences from language sequences. And we can directly utilize that to generate the actions as well, partially because these actions, they have a lot of connections to the text sequences as well. You can see in the previous example, some of the labels just are literally the text labels. So, so this shows a way of modifying the transformer architecture with attention to combine with some kind of graph construction process autoregressively. And later we also saw this approach. So these graphs or our approach has some applications, for example, in some kind of knowledge-based question answering for applications aligning with neurosymbolic AI. So basically you can represent the natural language queries with some kind of semantic graph, and then you can also translate that into some kind of structured query graphs or language and interact with the database, or you can do a lot of these graph transformations and so on. So this mechanism provides a general kind of text to graph generation framework. So we show this example of generating semantic graphs like AMR graphs, but also it applies to different types of graphs. For example, some executable semantic graphs or program graphs. So some programs, they can also be represented as some kind of graph structure or data flow structures. So we actually applied this to different applications, like in task-oriented dialogue. So in some of these systems, you can just they can just be achieved by some of these function flow graphs. So for example, you ask the system a question at a pool party with Barack Obama and Joe for tomorrow at 9 a.m. And then you can translate this sequence to kind of program represented by a graph. Each node here is a function with their argument. And this program can be executed. For example, I can go to the database and find the calendar of Barack Obama and then confirm. But then in the middle, in the execution process, this could be slow because you have to wait for the program to be executed. So we actually propose some kind of generation paradigm, which to do this, semantic interpretation or graph generation or function generation online in the fashion that when the speaker is speaking, we simultaneously interpret their intentions with this programs so that we can catch the program and execute their results even before the user finishes speaking. So this is still based on our kind of detailed technique of generating graphs, but also incorporating this online component for this dialogue applications. And it can improve efficiency also with balanced accuracy. So here's a brief summary of this part. So we can generate, we have a general framework for text to graph generation. So basically formulating this problem to autoregressive generation problem, similar to how you generate language with these models, and also incorporate some of the structural information of the incremental graphs into the model, for example, in the attention layers, so that we can guarantee their faithful generation. So if more details, if you're interested, you can check these papers. Okay, so these were all interesting, but they were before the LLMs era. So nowadays we can even directly use this large language model to generate all kinds of these different graphs. So the quality is another thing, but they're certainly capable because they have seen the data like this. So now we switch back to the language generation problem, where we touch on the exciting problems of LLM inference, including how to improve the inference efficiency, as well as making these models able to dynamically incorporate external knowledge. So how did the language model do the generation? So we saw this before. So basically, they model a bunch of these predictive distributions, and then they can generate tokens one by one. So for to generate n tokens, so the language models need to run n times sequentially. So this is sometimes very expensive because you have to wait for the last token to generate until to generate the next token. And also these models after they are trained, it is very expensive to adapt these models new domains or update their parametric knowledge, or work with private data, because these models, as they become more and more gigantic, it's just infeasible to update them very often. So so there's some solution called retrieval augmented or retrieval augmentation. So they augment these language models with an external database. So these databases can be from different domains. They can be dynamically updated. They can be private information, and so on. And during the inference time, by inference we mean generation or decoding, you can combine the neural language model generation with this external database. So no training is needed, and this is a non-parametric method. So you just do the search, and then you feed the information to the language model, and it can reduce hallucination in many scenarios because you just provide the most up-to-date information to the model. So with that context, so here's a motivation of one of the novel approaches we propose to modify the generation process to help it to become more efficient and also more adaptive. So if you look at some of these, if you interact with these models, you look at how these models respond to users when you ask questions or similar questions. So even if, because the model intrinsically samples from the probabilistic space, so even if the model gives you slightly different answers with these variations, there are some of these key components. For example, if you ask the answer to the life in the universe and everything, it is 42. So it always gives you 42, even if the framing of the whole sentence is different. So even with the variations, there are certain knowledge beyond the token level or on the span or n-gram level that stays kind of the same, and model memorizes these kind of information. So why do we need the model to generate the same text or same chunk of tokens every time, token by token? Isn't that a waste of compute by autoregressively generating tokens? How about we can extract these text chunks and store them along with their context? And then if we see similar context, for example, to the question, the answer to everything in the universe, we can directly retrieve this information, usually expressed in multiple token spans. And by doing that, we can save compute during the inference time. So depending on how we can extract these chunks, so they kind of inject the knowledge into the distribution during inference time. So this deals with the quality problem generation. And by retrieving them and generating multiple tokens at one step, we can increase the efficiency of these language model generations. So here's a closer look at these kind of LLM distributions. So if you let the LLM run on some sequences and output the scores of the sequence, so these are predicted distribution over the sentence, the answer to life, universe, and everything is 42, and so on. You see this kind of high probability plateaus at these structures, the multi-token chunks. So it seems that the LLM learns to bind these tokens together when they express some kind of semantic syntactic structures, or they contain some intensive knowledge that's less variant. So which is also not surprising because if the model is good at generating a lot of knowledge, it should be able to do this. This also provides us a natural way of extracting these sub-sentence level knowledge from the language model distributions. So we propose the chunk-distilled language models where we can first run the model to extract these knowledge-intensive chunks on some documents based on the probability distribution. So this kind of builds some kind of self-memory from the model parameters into some explicit memory. And then during generation, if we see similar context, we can go back to the database and retrieve the chunk level information and interleave that with the generation. So in this,
put the context to search for in this.
we'll get to that. So basically we do some dense retrieval based on the hidden states of the model itself. We'll get to that. So in this case, if you retrieve some structure of multiple tokens, you can also save compute because now instead of feeding one token at a time, you feed two tokens at a time. So this increases efficiency. And about quality, so if you just extract the information from the model itself, it doesn't change the distribution. It can at most approximate the previous distribution. But you can also extract the knowledge from a different model, like from a larger model, from a more domain-specific model, from a private model, or even from human beings. You can define these chunks yourself, like from Wikipedia, hyperlinked text. So in this case, if you inject this information or knowledge during inference time, it can also improve the quality of the generation by influencing the distribution. So under CDLM, we actually depend on where the chunk knowledge is extracted. We can have different variations of these generation strategies. Basically, you can distill knowledge from itself. We call self-distillation. From a better model, we call it knowledge distillation. Or from a human expert, we call it expert distillation. So here's some brief comparison with previous approaches. So there exists in many works to trying to improve the inference efficiency and also adaptive ability of the model distribution at generation time. But most of them just deal with one at a time. Whereas in our approach, we can both speed up the generation and also affect the model distribution with the same method. So for a rough procedural description for the CDLM inference, we have to first extract these chunk database, and then during the generation, we can run the LLM to do its own generation, and then search the token chunk database and match context. And whenever there's a good match, we can directly insert or interleave the generation to the model. So for example, here, let's say we have this database. So we use prefix tries, which is an efficient data structure to store these token chunks. And we let the model start the generation, the answer to everything. So here, everything, we know this everything. We can match this to the root of some token try. And so for the search, we actually use the hidden states from the language model itself. Because when we build the data store, we also save the context represented by a vector. So we can do the vector search. Whenever there's a good match, we go down the try, retrieve the token chunks. In this case, we have two tokens together. And for the next step, these tokens can be directly input to the LLM. So you don't have to generate them token by token, wasting compute time. And then you continue the process. And then for the next time you hit another match, you can retrieve the full structure. And then you save a lot of compute in this time. And depending on where you extract the knowledge, so the distribution could also be changed because of these external injection. Distribution doesn't necessarily have to follow the LLM parametric distribution learned from its pre-training. So we did some a lot of experimental studies to show to see how effective this approach is. So one thing, remember, we improved the efficiency for the at the beginning. So one thing is that we can save more token decoding time represented by these metrics, average token time saved, and also more intrinsically average forward pass save. A forward pass, which means basically the pass from the input to the output. We can say with our approach from on these different LLMs, we can save different percentages of time. And here are some kind of more straightforward illustration of how this generation approach behaves. So basically, so here are some hyperparameters controlling how frequent you can retrieve the sub-sentence level knowledge chunks. And with the red marking the tokens that are being retrieved together. So we can see that actually they're pretty fluent based on our design, and they can, the more red we have, the faster the generation will become. So here's some more intrinsic evaluation of the perplexity, which measures how well the model distribution fits some real world data. So in our case, we can achieve fairly good performance in adapting the model distribution to some domain-specific data without training. So everything is just through this inference time injection of chunk-level knowledge. And I'll skip this and some human evaluation on the fluency as well. So basically here, we've introduced this chunk-distilled language model, or CDLM, which interleaves this fine-tuned, fine-grained chunk retrieval with LLM generation. And it can improve both the generation efficiency and also the distribution in adapting to external knowledge. In the last part, we're going to talk about move from language generation a little bit beyond to, still language generation, but taking multimodal information. So in this case, we're going to talk about some algorithm that we propose to reduce the hallucination in vision language models. So here's a brief overview of vision language models. So basically, it can still generate language, or sometimes also images by taking different inputs of language instructions and the images. So here's the typical structure of a vision language model, in short, with VLM. So usually you still have the language model decoder, but instead of only having the prompt representing language, we also have some prefix in the prompt representing the image information. So we call these image tokens. So they usually come from a vision encoder that starts with the image, and then after projection layer to transform the visual representation to the input space that's expected by the language decoder. And usually we can use large language models to initialize these language decoders and with some pre-trained vision encoders. And we only need to adapt these projection layers in the simplest case. But their generation is not perfect. So here is an example. So here's the image. And if you pass this to some visual language model, it could generate a man is holding a surfboard on the beach. And obviously, this is wrong. So if you look closer, the man is not holding a surfboard, it's holding a clock. But because the language model has, or data we have a lot of prior, so we'll associate beach with the surfboard and so on. So the dependence on these language prior or language prefixes would maybe dominate the generation for the next token. So we want to have a way to correct these generations or reduce the hallucination. So this is called object hallucination. Reduce the hallucination to decode from the image. So here's some kind of simple study. So we hypothesis that the hypothesis is that if we look closer to the image, whenever we want to generate the object the man is holding, maybe we can look closer to the part that the man is holding something and see if that can help us correct these errors. And actually I found that's a pretty effective way of correcting these hallucinated tokens. So basically here are different types of hallucination, and then y-axis is the kind of percentage of the hallucinated token. So when we kind of manually feed in select these image regions for different position for generations, we can see the hallucination largely is reduced. And also if you feed in these different kind of image regions of interest, or we call visual context, you can see the probabilities of these different tokens, either hallucinated or ground truth tokens, are changing. So we want to find the visual context that best map to the ground truth token. So that's the motivation why we will come up with the algorithm called adaptive focal contrast decoding. So this is a rather complex figure, but I'll quickly walk through the intuition behind this because of limit of time. So basically at every step, we can let the model do the decoding, and then we can identify, okay, here the current decoded token is an object, so it may suffer from object hallucination. And then we go back to the model, actually go back to the image and try to identify the region of the image that is closely contributing to this current decoded tokens. And based on that region, we can sample a bunch of different visual context regions because we don't know what is the ground truth. And the best we can do is probably sample a bunch and then check their distribution differences. And maybe, from their contrast of different distributions based on these image regions, we can extract useful signals to correctly generate the next tokens that are faithful to the image. And finally, we do some global beam search to better align these generated sequence to the image. And basically, we run this on many standard object hallucination benchmarks, which are roughly measuring how many objects you generate are hallucinated, along with the quality of the generation to describe the image. And we found that our approach mostly reduces these hallucinations on different objects, on different benchmarks. And here we can even show some examples. So the first one is our model generations. So it's a Mona Lisa. And here the red text marks some of these hallucinated content for this image. And the Grady decoding just means sampling from distribution by taking the argmax token. So it says she's wearing a necklace when she's not. And in our generation, basically, these hallucinated tokens are not existing because we do kind of more fine-grained check on interested image regions for every step generation. Here's another example, and here's another example. Basically, these VLMs can take in images of different styles due to their training. So in this case, standing in front of a building. This is not obvious. Actually, I can't see the building, but if you go back to the image and then reuse different visual context, you can eliminate that kind of hallucination. There are also similar approaches that try to, for example, mask different parts of the image and try to get the language generation prior and then contrast the language prior with the image prior and so on, which are all related works. So as a summary, to reliably generate language from these vision language models, we propose this decoding algorithm based on intuition that we can just zoom into the image and maybe find more relevant image context that can come back with this language model prior in the decoding time. So again, everything is around decoding and generation, so there's no training is needed. More information, details can be checked in the paper, which was from this year. So here's a recap of what we talked about of different generation approaches and different applications. So first, we talk about this text-to-graph generation, a general framework utilizing encoder-decoder transformers and pre-trained models. And then more relevant to the current large language model, we talk about a novel kind of decoding approach by utilizing retrieval and chunk level decoding to both speed up the generation and also incorporate dynamic knowledge. And finally, we talk about reliable multimodal generation. So again, back to the initial question. So LLMs, we call it LLMs, but now the application and scope of these models are already way beyond language itself. By just formulating this next token prediction paradigm, these are actually general models on sequences. For example, you can generate code, images, audio, and even video based on how you sequentialize or bring the problem to kind of some formulation that are closer to this language sequence generation. We also tried different using the kind of LLM language modeling approach, different data modalities. For example, one effort was on these kind of network data. So we want to model these time series of network traffic so that to build a model that's pre-trained on a lot of these time series data to generate semantic representation that can be fine-tuned for different downstream tasks, where we kind of adapted how to represent the feature, how to discretize them, and to utilize the transformer architectures. And more general to the current landscape of natural language and generative AI research. So here are a lot of questions that could be interest to study. For example, we can gain better understanding of these large language model, multimodal models in a way that can improve how these models can be applied. For example, we can do a lot of analysis to understand how these models intrinsically work. And we can design extrinsic evaluation benchmark towards harder corner cases to get a sense where the model fails or towards next generation of these AI models. And then to improve these models, I've already showed a couple of approaches that can improve the efficiency and quality. And there are also a lot of efforts in modeling the reasoning ability or making these models very, very good reasoners towards harder math problems and etc. And intrinsically, we also, no matter what we do, we want the model to be trustworthy so that we can trust them in actual applications. And we're moving towards these language applications plus different modalities of data and even different application domains like science, network, systems, and so on. So these are all, there are a lot of interesting problems, and my broad interest lies in these kind of domains, like how do we understand them, how do we improve them over different axes. So with Stony Brook NLP group, it is actually growing. So we have many faculty members and a lot of students. So if you want to interact, you could also check the updates and maybe join the reading group and see papers, or bring to the discussion. So if you want to get involved, I'm also kind of using an NLP Slack workspace. So I intend to build it to more general to the NLP community we have in Stony Brook. So if you're interested, you could also join the workspace where we can have more kind of timely discussion and share of information. And also in the next semester, I'm going to teach a class around some frontier topics in large language models. But I still have more information to be updated. Cool. Yeah, thank you. Any questions?
No, thank you.
Okay.
In case of constraint text generation,
Mhm.
how do you design the algorithm to like enforce the model to like very strictly follow someone? Like, if we want to generate a text, like we input the text and we want to generate a text that has a similar meaning, but it should be like valuable.
Right.
These type of strict constraints, how do you like? Many people have designed a decoding strategies and some loss function modifications. How do you see it like changing the model or making the model to predict this strategies?
Yeah, that's a great question. So you want the generation to follow your constraints. And I would say typically nowadays what people do is to describe the constraint in the prompts, so that you don't have to do any interference with the model and so on. So that's the ability people build in this model through instruction tuning, so that they make model respect the prompt. But still, there's no guarantee. So I think there's a lot of room to improve as well. So first, I think we need to get a better understanding in what cases the model would fail. In what cases, probably in a lot of cases, they would follow instruction pretty well. Yeah. Yeah.
So you might have covered this during the presentation, but I'm just wondering for the chunk-distilled language modeling, how do you do the chunking and then on what kind of data set? Is the data set similar to the training data set or it's like a totally different one?
Yeah, that's a great question. So if you remember the example I showed there, so basically, for example, in the case of self-distillation, we want to build the data store in a way that's close to how you would apply the model to, right? Right. So in a specific domain, for example, in this case, if you know, like you're gonna ask anything, like a lot of things about these books, you could extract questions about these books and let the model first do the generation, and then we can use the model distribution to extract these chunks. So it's kind of so it's not exactly like disjoint kind of training and inference. We don't have training, so our philosophy is just to facilitate acceleration. So the closer the data store to your testing time, the better.
But then there is like big processing step you have to do.
Right. Yeah.
For each specific application.
Right, yeah. So that's similar to the retrieval applications. You always have to build the data store. And so that inference time, it could be they could be used. Yeah, yeah, yeah.
So this chunk idea, this basically, if you can look at it in this following way, right? So these earlier, I mean, before, so now the tokens, one problem with language modeling some time back was the vocabulary size was very large. So people reduce the number of tokens to a very limited number rather than having all possible words as the vocabulary, right? And your chunks are like basically words which were basically individual elements of vocabulary in some of the earlier models, which were difficult to train. So you are basically having these words or basically chunks of tokens which occur frequently together and whose probability of occurring together is very high, and you are just catching them away. I mean, is that
right? You can also think about, because they're retrieved from database, you can think about database of chunk as an extension of the vocabulary, which is kind of dynamically adjusted based on how you build them.
Right.
Yeah, and you don't have to train with them, because that's the whole idea of retrieval.
The training you are still doing on only those 30,000 various on the 30,000 tokens, which are less than the total vocabulary of the language.
Well, the training is whatever the pre-trained LLMs, whatever they have. We don't do any training.
Okay.
So. More questions? If not, yeah, thanks everyone for coming. Yeah.